Hello, one more time. We're in Chapter 1, Section 9, Introduction to Parent Functions. And this time we're doing problem number 10, which is the application problem. All right. So a pendulum is a weight at the end of an arm or a string. And as you pull it to the side, gravity pulls it down and it swings back and forth. I'm recording vertically. So like if I did a pendulum, you wouldn't be able to see it. It would do like that, okay? So, but you'll just have to take my word for it, okay? The time it takes a pendulum to make one complete swing back and forth depends on the length of the string. These are things that are kind of important in physics. So first of all, what we're going to do is we're going to graph the relationship of how long the string was and the time it takes for the pendulum to go back and forth. I guess I can kind of draw it. So we have a mass of something at the end of a string, and then as I pull it this way, I'm going to let it go, and it's going to swing back and forth from here to there, back and forth like that, okay? So how long in time it takes for it to go from starting position back to center and over to the other side, we're saying kind of depends on how long the string is, which kind of makes sense. Short string, it wouldn't take that long. Long string, it would take longer. Of course, there's other factors here, and if you're really smart, you're paying attention to those, but for now, just roll with it. So I'm going to graph this. String of the length 2 takes 2.8 seconds. Now look at my scale. My scale goes from 0 to 10. This will be string length in meters. So these are long strings. And this will be the time in seconds. So 2 meters is going to be 2.8. That's just below 3. So this goes 1, 2, 3, just below 3. 4 meters is going to be, looks like 4.0. So that's going to be right here. 6 meters is going to be 4.9. Here's 6. 4.9 is just below 5. 8 meters, here's 6, 7, 8, will be 5.7, which is just below 6, about right here. And 10 meters will be 6.3, which is just above 6. All right, now that looks like it could be linear. And notice I did approximate, but like I did earlier, I don't know. I don't think it's supposed to be a line. I think we can also assume that if the length of the string is 0, which doesn't make sense, but if the length of the string is 0, then the time would be 0 because you wouldn't have a string. So we have some place to start. I'm just going to assume that that's true, and it might not be. But now it kind of looks like my graph does this kind of a curve. And if I match that up, it looks like we might be getting into this section. What parent function does this look like? Try to get everything in here. Yeah, maybe not, might not work. So which parent function best describes it? Looks to me like it's going to be the square root function. And of course the family, square root. Now we're going to use the graph to estimate how long the string is if it takes 4.5 seconds. Let's go here. 4.5 seconds is right here, 4.5. And if I come over, well, it looks like right about here maybe, which would be about 5 seconds. So this symbol right here, that squiggly line, it's called the tilde. That's our symbol for approximately. So we're going to say approximately 5 meters. And the last one, use your graph to estimate the time it takes to make a complete swing for a string of the length 14 meters. Well, unfortunately, my graph didn't go up to 14, but I can kind of pretend if I went over this way, here's 11, 12, 13, 14, and it looks like my graph is doing this. So if I go up right about here, come over, yeah, you can still see that, come over here, 5, 6, we're going to say about 7 seconds. Now, I did this on paper because I wanted you to see both of it, but this would totally be something that I could also do on Desmos, in which case I wouldn't be constrained by the paper. Okay, we'll talk in class.